Hi everyone. In today's session, we'll see the three-phase semi-controlled rectifier control of separately excited DC motor. So in the last session, we have seen three-phase fully controlled rectifier where each leg has two control switches, total of 6 switches. So in semi-controlled rectifier, the positive group switches which are connected to the positive common cathode switches are connected to the positive are called the positive group switches. The positive group switches are the control switches. The common anode is connected to the negative group. The corresponding switches are called the negative group switches. The positive group switches are 3 control switches and negative group switches are 3 uncontrolled switches, diodes, placed to get the semi-controlled rectifier. So here the corresponding phases are A, B, C and the corresponding phase currents are IA, IB, IC. And the load equivalent is motor equivalent load RA, LA and back EMF E is connected to the semi-controlled rectifier, where the corresponding output voltage is V0 which is equal to the armature voltage and the corresponding current is IA is equal to I0. The semi-controlled switch will give the single quadrant operation because both voltage and current, obviously the current is always positive, it will come out of the common cathode only in all the rectifiers, but here the voltage is also positive because as this is semi controlled rectifier, by varying the firing angle from 0 to 180 degrees your voltage is always positive only. That's why it works only in the single quadrant. On the V0, I0, y axis and x axis if we take, it will work like a single quadrant switch. Hence you will get the speed torque characteristics also in the single quadrant. That is nothing but forward motoring characteristics only you will get by using this 3-phase semi-controlled rectifier drive. Okay. Even in the previous videos we have seen how to draw the 3-phase waveforms also. Even in the 3-phase rectifier also we have drawn complete 3-phase source voltage waveforms for more number of cycles, but here for simplicity and to show more clearly, so I have taken 3-phase waveforms only on the positive side because anyway we will get the voltage only on the positive voltage, or on the positive side waveform only will get it as a output voltage. That's why here I have considered only positive side voltage waveforms. However, you need to draw the complete waveform in exams. So here if you take the source voltage waveform, to draw it faster I have divided the omega t axis into 60 degrees equal intervals, and by drawing the triangle and by joining the edges of the triangle with envelopes, we can get the 3-phase voltage waveforms. Here the dotted line shows that this is VCB waveform, right? This is VCB waveform, this is VBC waveform. The VBC waveform will continue like this. So the VBC on the negative side, if it is reflected on the positive side, that will become minus VBC. Minus VBC is nothing but VCB, which is denoted with dotted line. In a similar way, this is VAC waveform. The solid line is VCA waveform. This is VCA waveform. It will come like this, VCA. So from here to here, that is reflected on the positive side with dotted lines. VCA on the other side is nothing but minus VCA. So VAC is equal to minus VCA. So on the negative side voltage waveform we are reflecting on the positive side. So that's why it will become minus VCA, which can be rewritten as VAC. Okay. In that way I have drawn all the dotted lines for the negative side voltage waveforms are reflected on the positive side. Now in the 3-phase semi-converter, here we are having only 3 control switches. When we are having 3 control switches, the angle difference from one firing pulse to the other firing pulse is 120 degrees only, because Total cycle is 360 degrees is divided by 3 control switches, which is equal to 120 degrees. So this is the angle difference from one firing pulse to other firing pulse. Even in 3-phase rectifiers, 360 degrees by 6 control switches we have. 360 degrees by 6, which will give 60 degrees. That's why in 3-phase fully controlled rectifier, the angle difference from one switch to other switch is 60 degrees. If you take single phase rectifiers, the single phase rectifier is having, even though the pair of switches we need to consider there. Two pair of switches need to conduct at a time, right? So likewise in bridge rectifier we are having two pair of switches. Likewise two pairs are there. So total 4 switches. So 360 degrees by 2 pair of switches. That is equal to the 180 degrees. That's why the angle difference between the one firing pulse to other firing pulse in single phase rectifier is 180 degrees. Even in single phase semi converter also there are two control switches. 360 degrees by 2, which is equal to 180 degrees angle difference from one firing pulse to other firing pulse. So anyway, here in the 3-phase semi converter we are having 3 control switches, 360 degrees by 3, which is equal to 120 degrees angle difference from one firing pulse to other firing pulse. How many firing pulse do we require here? Here we required 3 control switches, 3 firing pulses required. So which is the more positive voltage here? The positive voltage will start from VAB. VAB is more positive voltage than the other other line voltages at this point. That is equal to the omega t is equal to 60 degrees. On omega t axis, this is 60, 0, 60, 120, 180 likewise. So at omega t is equal to 60 degrees, the voltage waveform is more positive. Hence, from there onwards, you need to provide the firing pulse to the switches. That's why this is nothing but alpha is equal to 0 point. So if alpha is equal to 0, if you consider, if you want to give the firing pulse at alpha is equal to 0 means T1 switch need to provide the firing pulse at 0, alpha is equal to 0, the correspondingly omega t is equal to 60 degrees. After 120 degrees, you need to provide the another firing pulse. Each envelope is equal to the 60 degrees here. So that's why this equal to 120. After 120 T2, then after 120 T3, then after 120 T1 again, that will repeat, because if you see here this is 60, the corresponding T2 is at 180. 180 minus 60 equal to 120. The angle difference between the one firing pulse to other firing pulse is equal to 120. So in this way we need to provide the firing pulses. So here we'll see the firing pulse sequence, then only we can draw the output voltage waveform properly. First we need to draw the firing pulse sequence. Let's draw the waveform for alpha is equal to 60 degrees. For alpha is equal to 60 degrees, so the positive group switches are T1, T2, T3, because common cathode is connected to the plus. And negative group switches are, here common anode is connected to the negative or minus. So D1, D2, D3 are negative group switches. So T1 should start at alpha is equal to 60 degrees, right? Because for alpha is equal to 60 degrees, we are drawing the waveform. For alpha is equal to 60 degrees means this is alpha is equal to 0 point. From here onwards, we need to take 60 degrees. Alpha is equal to 0 onwards, we need to consider the 60 degrees. So this will become the alpha is equal to 60 degrees point. So at here onwards, alpha T1 pulse will start. So on omega t axis at 120 degrees T1 firing pulse will start, and it need to continue its conduction till 120 degrees. So 120 plus 120 is 240. Till 240 T1 firing pulse or T1 need to be in conduction. Anyway, thyristor will have short pulses only, but T1 will be in the conduction till 240. After 120 degrees conduction of T1 thyristor, the next T2 thyristor need to start. So T2 has started, then T2 will be in conduction for 120 degrees. After that T3 will be in conduction. Then after 120 degrees of T3 conduction, then T1 will start and it will be repeated. So before T1 also it will be T3, like in this loop. So before T1 T3, right? Before T1 T3 for 120 degrees. So if you see the negative group switches, these are diodes. Irrespective of the firing angle, the diodes need to be conducted, or diodes need to be have its conduction the same conduction will be there irrespective. For alpha is equal 60 degrees, it will be the same sequence. For alpha is equal 120 degrees also the same sequence, because these are the diodes. Based on the firing pulse, the diode sequence will not change, because if you see here, the VCB is more positive at this point, because this is 60 degrees, right? VCB is more positive. So how to identify the negative group firing pulses or negative group switches? Based on the second subscript, right? Based on the second subscript means the VCB and VAB, right? In both the 60 degrees intervals, out of this 120 degrees, the first 60 degrees is VCB, second 60 degrees is VAB. Up to 120 degrees, B is the second subscript. B is the second subscript means, what is the B phase? B phase is connected to which diode or which cathode of the switch? The cathode of the switch is nothing but D2 switch. So B phase, right? First subscript indicates that need to be connected to the anode of the positive group switches. Second subscript denotes that should be connected to the cathode of the negative group switches. So here VCB means B phase, negative group switches is D2. Here VAB means VAB, right? Second subscript is B again. So B phase is connected to the cathode of the again D2 switch. So here also the switches need to conduct for 120 degrees only, even diodes also. So diode D2 will start conduct from omega t is equal 0 onwards to 120 degrees, because till this 120 degrees your second subscript is continuing, right? Then after that, if you see from 120 to 240, VAC and VBC, in both the cases C is the second subscript. If you see the C phase negative group switch is nothing but D3, where cathode is connected to the negative group switch diode D3. So D3 will be in conduction. Then after that, from this point, from 240 to 360 degrees, VBA and VCA. VBA and VCA. A is the second subscript. That means we need to see the A phase. The corresponding negative group switch is D1. It will be repeated again D2, D3 from negative group switches. So because the source voltage waveform do not change, always VCB, VAB, VAC, VBC, VBA, this is the sequence. Hence your diode sequence also in the same way, but for the positive group switches will be turned on at different places based on the firing pulse. If you are providing the firing pulse at alpha is equal to 0, VAB is the first voltage waveform, it will follow the VAB. Otherwise, if you provide the firing pulse at 60 degrees, the waveform shape will be different. This will be skipped, right? So if it is 120 degrees means that will be different. How it is different, that we'll see through the waveform. Anyway, these firing sequences are for alpha is equal to 60 degrees. So by seeing this firing sequence, if you see here, for first 120 degrees, the switching sequence or switching pairs are T3 and D2. From positive group, T3 switch need to conduct, and from negative group, D2 switch need to conduct. So T3 corresponding phase is C and D2 corresponding phase is B. So as positive group switch is T3, that's why VC, first subscript is C, and negative group switch is D2, that's why it will come as a second subscript, VCB, right? So it need to follow the VCB voltage waveform. So it need to follow the VCB voltage waveform from here to here till 120 degrees, where T3 and D2 switches are turned on. Next, for alpha is equal to 60 degrees only we have taken here, that's why T1 switch is conducting from here. So T1 in combination with D3, right? So T1 is the positive group switch and D3 is the negative group switch. The T1 phase will come as a first subscript that is A, and D3 switch will come as a second subscript, that is C, because D3 is connected to the C phase and T1 is connected to the A phase. So V, A and C. So it need to follow VAC waveform during this T1 T1 and D3 combination. Where is VAC? This is VAC. This dotted line to here like this. So VAC. Next T2 and D1. So T2 from positive group switch. That's why it is VB and D1, right? So D1 means it is negative group switch A as a second subscript. VB and A. So it need to follow the VBA waveform for this duration. VBA means this dotted line. So VBA, and it will continue again VCB and VAB. This is the one complete cycle, right? Up to here it is one complete cycle. 120, 120, 120, 360 degrees. So assuming the continuous load current, you are getting the continuous load current I naught. And if you see the difference waveform for alpha is equal 90 degrees, let us take alpha is equal 90 degrees. If you take the alpha is equal 90 degrees, the firing sequence will change a little, because T1 instead of starting from alpha is equal 60, it should be 90 degrees, right? The mid of the from peak to x-axis, it is 30 degrees. 30 plus 30, 60. This is out of 60. Equally it will be divided, so it will touch at this point. So this is nothing but 30 and this is nothing but rest of the 30. So by drawing that line, so we need to take alpha is equal 90 degrees means this is 60 degrees, 60 plus 30, 90 degrees. 90 means here I have considered one point, and from here onwards your T1 will start its conduction and it will continue till 120 degrees. So this is 30 and 30 plus 60, 90, again half of this duration, that is equal to 30. That's why it is equal to 30 plus 60 plus 30, 120 degrees. After this again 120 degrees T2, then 120 degrees T3, and it will be repeated. Whereas D2 diodes sequence, if you see D2, D3, D1, it will be same D2, D3, D1 only, because those are uncontrolled switches. We cannot control the diodes by changing the firing pulse. That's why the diode sequence is same. But by taking this, the combination of switches will change. By shifting the firing angle from 60 to 90 degrees, the combination of switches will change. Earlier T3, D2, T1, D3, T2, D1 are the combination of switches turn on. That's why you got the output voltage waveform like this. But now the combination has changed like this. For first 30 degrees, the combination is T2, D2. And next T3, D2. Next T3, D3. Next T1, D3. Likewise. Anyway, first for alpha is equal 90 degrees, the first switch is T1 is combination with D3 for how much duration? This is 30 and this is 60. So total 90 duration, 90 angle difference, you will get this waveform. T1 is in combination with D3 means T1 should be connected to the A phase. So VA and D3, right? C. VA, C. It need to follow the VAC waveform again in a similar way, VAC. So VAC, source voltage waveform here, the dotted line, VAC for 90 degrees. So VAC, this is 30 and this is 60, total 90 degrees duration. Next, if you see T1 is here and D1, T1, D1 both are from the same leg. So the T1, D1 both are from the same leg means simply your load will get short circuit. T1 and D1 both are from same leg. So that's why your load is getting short circuit. That's why here the output voltage is 0. When the same leg switches are conducting, your load is getting short circuit. Next T2 D1. When T2 D1, VB and D1 A. T2 and D1 VBA. It need to follow the VBA. So VBA is for this T2 D1 from here to here VBA, or just 30 degrees will be neglected. So if we remove the 30 degrees from the 60 degrees waveform, just we need to hatch this portion, then you'll get the 90 degrees waveform. So instead of having the waveform here you'll have the 0 degrees, because same leg switches are conducting T2 T1 D1, and here T2 D2, here T3 D3. That's why that 0 portion is coming, whereas the output voltage is continuous current only. Okay, so during the positive half cycle or positive voltage it will be charged, when 0 it will be discharge. Here also you have the discharge through the freewheeling path. This is nothing but freewheeling path through the same leg switches. Both T1 D1 are turn on, means the stored energy in the inductor will discharge through this T1 D1 combination. It will freewheels. That's why your output voltage is 0. Next, if you see the waveform for 120 degrees, alpha is equal 120 degrees, here you will get the discontinuous conduction, because alpha is equal 120 degrees means this is 60 degrees. From 60 to omega t, on omega t axis 60 degrees means that is alpha is equal 0 point. This is alpha is equal 0 point. From there onwards 120 degrees means it will go up to here. So from there onwards T1 will start its conduction for 120 degrees, and next T2, next T3 and so on from the positive group. And negative group switches, diodes will be conducted as usual like earlier, D2 D3 D1 only. Now you need to see the combination of switches. T2 D2 for first 60 degrees means this entire T2 D2 is a combination of 0 degrees, that may be free wheels or no conduction. So if we take the discontinuous conduction, let us see from the T1 D1 combination, T1 onwards. So here onwards T1 switch, right? So T1 means T1 is in combination with D3. So T1 D3 combination, you'll get the VAC waveform, but that combination is from up to here onwards only, from here to here only. That's why. So this is the combination. From here to here you'll get the VAC, and again after T1 D3, T1 D1 is a combination. T1 D1 means same leg switches. T1 D1 are the same leg switches, T2 D2 are the same leg switches, T3 D3 are the same leg switches. When same leg switches are conducting, simply your output will get short circuit, or it will freewheels its energy, or your current equal to 0 means simply T1 D1 will get short circuit like this. So this is the VAC waveform. Then T1 D1 for next 60 degrees, your T1 D1 is conducting, means during this positive voltage, if your inductor is getting charged and if your inductor is getting discharged in the next 30 degrees itself, means, or next any before 60 degrees, next before 60 degrees means somewhere it is discharging. So till that point only your load current is present. After that load current equal to 0. When load current equal to 0, what is the voltage across the load? The load is having the back EMF. The back EMF will be present in the output voltage. When the load current is freewheels through the corresponding T1 D1 switches, it will get short circuit. That's why 0 volts. Here it is 0 volts. Here it is E volts. Back EMF will be presented in the load voltage. As your load is getting short circuit, you got 0 volts here. But load current is not continuous. Load current is discharging up to this point only, which is nothing but load inductor current. So after this there is no current in the inductor or load. When there is no current in the inductor or load, the corresponding output voltage is equal to the back EMF voltage, because when I equal to 0, the corresponding output voltage is E, V naught equal to E. So in that way, the rest of the waveform simply will follow the VBA waveform here, because already we have seen for 60 degrees and 120, 60 degrees and 90 degrees, right? Simply from here to here, that will come as here. Then T2 D2 switches, same like switches, again charge and discharge. When it discharge up to here means when it is discharging it will free wheels, so your output voltage is 0 volts because it will free wheels through the one leg, that's why it is getting short circuit. Then next, when current equal to 0, from there onwards your back EMF will be appeared across the output. And next VCB, same voltage, and here it is VCB, and it will continue. This is for 120 degrees. So in this way we can get the output voltage waveforms. Once if you know the output voltage waveform and your output is periodical for every 120 degrees, earlier 3-phase voltage waveforms are 60 degrees interval, because your output is periodical waveform for every 60 degrees. Here it is for 120 degrees. So based on that, your output voltage equal to RMS voltage, output voltage equal to armature voltage equal to 1 by 2 pi by 3 integral alpha to pi VML sin omega t into d omega t. By solving this, you will get 3 VML by 2 pi into 1 plus cos alpha. Now you got the output voltage equation. As the output voltage versus firing angle, if you see, by substituting alpha is equal to 0 to 180 degrees, 0 means 1 plus cos 0, it will become 2. So 2 and 2 get cancelled, then 3 VML by pi is the maximum voltage. For alpha is equal to 90 degrees, this term will be 0, 3 VML by 2 pi. For alpha is equal to 180 degrees, 1 minus 1, it is 0. So from 0 to 180 degrees, your voltage is appearing on the positive side only. That's why your voltage is always positive in the 3-phase semi-converter. And obviously the current is also on the positive current only you will get it in the rectifiers. So by using this voltage as a firing angle relation, we will use the same equation in the speed equation. Speed omega m is equal to E by k pi, where E can be replaced with VA minus IA RA by k pi. I can rewrite that equation as VA by k pi minus RA by k pi into IA. So this VA can be replaced with this equation, then you will get 3 VML by 2 pi k into 1 plus cos alpha minus RA by k pi square into T, by replacing this IA with T by k pi from the torque equation. So here the no load speed for continuous current, because here in the 3-phase rectifier the discontinuous current effect is neglected. So we will draw the waveform for continuous current only. If you take the discontinuous current, the discontinuous speed torque characteristics or the discontinuous current effect will be there in the single phase rectifiers more than the 3-phase rectifiers. Because of the discontinuous current, your speed torque characteristics will start beyond the discontinuous conduction effect will be because of the speeds more than the critical speed. If speeds are more than the critical speeds at light load condition, you will get the discontinuous effect in the speed torque characteristics. At light load condition means in the speed torque characteristics during the initial torque from 0 onwards, during the light load condition, if speeds of the drive is more than the critical speed, then you can experience the discontinuous conduction. During the discontinuous conduction, the no load speed is equal to the E by k pi simply. During the discontinuous conduction effect, your omega m is equal to E by k pi, right? So here E will become Vm by k pi, because during the discontinuous current at no load will consider, at light load or no load. At no load means your E will become V minus IARA, right? That IARA drop will be neglected. So your E will become maximum source voltage is the EMF. By using this we can find out the no load speed. So from here omega m naught is equal to no load speed. So in this way we can get the no load speed in single phase rectifiers or three phase rectifier. No load speed during the discontinuous current is nothing but omega m naught is equal to Vm by k pi, where Vm is nothing but the supply voltage maximum voltage, because E is equal to Vm. So for continuous conduction, just you can keep the Ia equal to 0 where torque equal to 0. That makes the omega m as omega m naught is equal to 3 Vml by 2 pi k into 1 plus cos alpha. So by keeping this alpha is equal to 0 to get the maximum voltage, you will get 3 Vml by pi k. So if you draw the speed torque characteristics, speed versus torque characteristics for various firing angles from alpha is equal to 0 to 180 degrees, your characteristics will shift downward, because alpha is equal to 0 will give the maximum speed. Then as your firing angle is increasing, your speed torque characteristics will shift downward. But it will be in the first quadrant only. Your both speed is positive and torque is positive, hence it is in motoring mode. As speed is in the forward direction or positive direction, it is in the forward motoring mode. So these are the speed torque characteristics, speed versus torque curves of the drive, by neglecting the discontinuous conduction. Okay, so this is all about the three phase semi converter controlled rectifier for separately excited DC motor. Thank you all.